Hello everyone. Good day, good morning, good afternoon. My name is Sven Philips. I'm glad to see you around. I'm glad to see that you're connected. So I'm a structural geologist at Eliis, and I'm going to present this webinar here for the latest platform upgrades in PaleoScan. So thank you for joining in. Just before starting, so just explaining how this webinar is going to work. It's going to last for 1 hour, so it's going to be quite short. Maybe at the end we're going to have some time for some free questions. For this, I would indicate you to look at the chat or the question tabs of Livestorm. So you can use the chat if you've got some public questions that you'd like to address to me publicly and have some public answer from me. And you also have the question tab available. So today I'm just alone myself introducing this session to you, so I won't have any site support. So I will take time once in a while to look at your questions and try to answer them in here. So again, thank you for joining in. I will soon share my screen and turn off the videos to increase or to enhance the bandpass and make sure that your video is not slowed down by like me displaying my face in the screen. So let's get started. I'm going to share one of my screen then, and we're going to start by a quick PowerPoint presentation. So yeah, during the time we're in here, just can you tell me if you can properly see my screen over there? I guess so. So normally everything is going to be okay for you. I'm just going to put my Livestorm session on the side and turn off the video. Okay, so, and we're going to start with the title first. It's going to be better, maybe. So that's the title of my webinar. It's the latest platform updates. So what we're going to cover in this session is they are the latest improvement in PaleoScan, the latest additions in the software, the tiny tips and tricks that you may want to use at some point and that you've not discovered yet in 2020 and the 2020 version of PaleoScan. And just to go through this, we're going to use the platform of PaleoScan. So just for those of you who wouldn't know the main workflow of PaleoScan, but I guess you do. Here is again a quick review of how PaleoScan works. So we're starting here to the left, and we're starting with the inputs of the objects in PaleoScan. So most of the things start with the seismic block that you can see here on the top. Then we're importing some regional key horizons that we may want to use as guidance during our interpretation, or as constrained in the model grid that you can see here. And also if we've got some faults available, we are expected to import them to facilitate the interpretation. So in the second stage of PaleoScan, this is what you can see here. I'm just going to activate the pointer here. So we spend quite an amount of time in PaleoScan interpreting the model grid, which is the framework for the interpretation. So you can see these series of nodes that are populated everywhere in your 3D seismic volume. And we've got here a final geomodel that we build with the constraint that we made in the model grid. And then this process is iterative, because if you want to improve the geometry of your geomodel, you can, at any stage, come back in the grid and try to improve your structures. So this is a semi-automated workflow where the interpreter is expected to help PaleoScan refining the grid. And at any point, you can use your well data, if you have some, to QC what you're doing, and later on to QC what you have done. So, and this is the third step here, which is a general step where you're getting some outputs from your geomodel that are going to help your analysis and interpretation. So one of the first things you can create derived from the geomodel is a series of horizons that we name horizon stack in PaleoScan, and on which you can map like a series of attributes. For example, here we've blended some frequency attributes, some spectral decomposition attributes. Plus, you can create some geobodies using crossbar tools or using more manual methods. What you can also do is derive some volumes that are attributes derivated directly from the geomodel. And then later on, you can pass it on to reservoir engineering, or you can create geocellular model, such as the one you can see here, directly in PaleoScan. But for today, we're going to focus more on this workflow and on the tiny tips that we have. So, for example, I'm not going to talk about the wells, or not going to talk about the attributes of the geomodel, and I'm not going to talk about the geocellular model. I'm just going to talk a bit about the 2D workflow and the improvements that have been released on the 2D workflow. So this is why I've drawn a straight line here, plain line, dark and bold here, to make the difference between the general workflow here with 3D and the 2D. So the question is, like, what are the latest updates on the platform of PaleoScan in there? So the first thing you can visualize in this workflow is that, first of all, when you're importing your seismic volumes, then you can use some multi-parameterization to fix your byte ID differently according to the seismics that you're importing. It's supposed to help you a bit in case of multi-import. Then once your volume is imported, you can apply some volume despiking. So in case you've got some spike values in the seismic volume, for instance, to prevent PaleoScan from displaying, these strange color bars that are just blank because of some spikes in there, then you can despike your volume and remove the spikes. And we've got also some improvements from the structural interpretation that is supposed to be undertaken ahead of the model grid building and interpretation, because, of course, structural interpretation and the creation of faults would help prevent some wrong connection during the automatization process of the propagation of the horizons in the model grid. Then what we have new in there, we've got a way to build the model grid that is a bit different and a bit improved as well. We're able to create some horizons in the grid that are going to be tied to the faults that we're inputting. So we're going to say this in a few minutes. And also we've increased the number of nodes to populate the grid in case your hardware allows having a really dense grid to improve your resolution. And finally, for this section, we are also able now to create some multi-Z geomodel. That means that we're creating some discrete discontinuities at the fault locations. And we can also represent compressive systems with first faults. As for the outputs on horizon stacks, so now we're able to create some composite horizon stacks made of some horizon stacks. And you're going to see the use of it as well in my presentation. And we're able to increase the number of horizons in a stack up to 10,000 horizons if you need it at some point. And that's for the 2D. So in the 2D, we've performed a bit of improvement as well in the fact that when you're computing a model grid on 2D line sets, now PaleoScan is going to be able to directly link and connect the different lines together and the different similar reflectors pertaining to different lines together. And at last and not least, we're able to use the 2D lines in the calculator of PaleoScan, which was not available before. And oh yeah, maybe that's a good point for you if you're using some CRS and feeds, if you're working in the Gulf of Mexico and some other areas where you could be glad to use the CRS and feeds. Now we're able to master and to manage the CRS and feed in PaleoScan. So let's go for the live demo. I see that you hear me properly. Thank you, Steve, for telling me. And yeah, don't hesitate again if you've got some questions during this presentation to leave them in the chat, and I'm going to have some little pauses at some point just to check out your questions. So I'm now going to go into the Peloskan interface. And here we are. And what I'm going to do, this is, in this interface, almost a brand new project. I've already started to import some volumes here just to save some time, but I'm going to pretend I'm importing some 3D volumes again just to show you this option of multi-SIGWI import. So now let's say I want to create a project and I want to import several volumes that are in the Gulf of Mexico, but not on the same UTM zone. And I would like to put them together, and I would also like to use some CRS in feeds. So first thing, I'm going to go in the import option of PaleoScan, so which is available at different locations, but in particular in the main toolbar here, import SIGWI, and I'm interested in 2 volumes for now. So let's go for volume import. So this is the interface, not much changes apparently. I'm going to look for my volumes in there. So I'm going to start with the volumes from the Gulf of Mexico that are in here. Okay, and I want to import these 4 different volumes. I'm going to click open, so I'm going to enlarge the interface a bit further. And here are again my 3 volumes here. Yes, so Steve, I see your question about the 2D. It's going to, I guess I'm going to tackle this rather towards the end of the workflow. So you'll have the opportunity to again, well, I'll have the opportunity to come back on your questions. So no worries. So here I've got 4 different volumes, and you can see from the real header that I've got potentially different information, or these volumes are located into different zones. Okay, so this one, for example, my first volume here is going to be located in NAT 27 and in UTM zone 16, and this one is in feet, for example. So I'd have to indicate a CRS corresponding to this. Then for the next one, it's also an NAT 27 UTM zone 16. And for the next one again, here I've got something different, I believe, somewhere. So where can I see this information? Down there. So here, this one is in UTM zone 15 and not 16. See here, still in NAT 27. And for the last one here, it's a bit different. It's in the same area, but not exactly. And this one is in NAT 27 and is located in Louisiana State Plains. Again here, southern zone. So I'm going to have to set my options here in the import interface according to this. So here in the interface, the first thing I'll have to do for each volume, so I'm going to start again by selecting the first one in the list. I'm going to have to go and hit the byte ID detection so that PaleoScan can recognize or try to recognize the byte ID information automatically. So I'm going to go on for it. You see that PaleoScan has detected that the ID here are different from the one automatically set. And once I've done this automatic byte ID detection, I will go into the lattice tab down here to the bottom right, check dimensions, and I'm going to have a scan of this volume just to see if the dimension that PaleoScan outputs are proper. So here is the result of the scan. So you can see that the inline step is 87.5 not meters, but feet, and about the same in X line, and vertical step is 4 milliseconds. So the first thing I'll have to do is to correct for this unit that is not meter, but in feet, of course, because I'm in the Gulf of Mexico here. So I'm going to go back here in the unit tab over here and make sure that the special unit is going to be adapted for foot. Or let's say I'm picking foot US here. So again, I'm going to go back and check dimension. Hit a scan again, and you notice here that the unit has been updated. Now, assuming that all my volumes have the same byte ID and the same unit, and the same, let's say the same CRS that I didn't apply yet, same SRD and same options. So SRD is irrelevant here because I'm working with a time volume, so I'm not going to fill in this case. But I'll be able to hit these apply segue import parameters to all. Okay, which is supposed to help me to save me some time if I assume that all the 4 volumes I've got in my list are set the same way. But first, as I say, this first volume here is defined in UTM zone 16 feet, so I'm going to have to look for such a CRS in my list. So here I'm going to play with 16 north and see what's, with the filtering, what's in the list available here. I'm going to go for NAT 27. And NAT 27 here, for example, I've got this one here, zone 16, and I've got zone 16, so it's not in UTM here, so it's BLM. I'm going to go for UTM zone 16. So let's go for this one. And okay, just let's say I want to apply the segue import parameters to all. I'm just hitting the button down there I was talking about. And now if I assume that all the byte ID are the same, I can leave the byte ID checked, the CRS checked, but I know that the CRS won't be the same in this case. We've seen this together. There's going to be one in UTM 15 and one in Louisiana State South. So I'm going to untoggle this one. Resolution, this is the decimation I want to use in there. So right now I've not been into the decimation, and I want to preserve my maximum resolution. SRD is not applicable. Units are supposed to be the same. I'm importing volumes that are all in feet, and zone of interest, I don't care about this one here. And I'm going to hit OK now. So now when I'm going to check at my other volumes, so for example, the second one here, then if I'm going to unit, you can see that the spatial unit is already in foot US. The CRS here has been set still the same. I'm just wondering why, by the way, because I didn't check this out in the list, but let's say this one is still in 16 north. Let's say, by the way, instead of UTMs on 16, I want to use something which is actually really in feet. I want to use the BLM CRS. So again, I'm going to have to enter 16 north, nat 27. And this time I want to use this one because it's in feet US, just to show you actually that we're managing this CRS in feet. So you see that the zone that is pointed out in green and the map is over here. Okay, for this one, just checking the option are still okay. So this is decimation that you find under option, and check dimension. Let's go for it. So you see that this volume here has a different resolution in X line. And I'm going to go in the list. So this one is in UTM 16. So let's go for UTM 16. I'm going to change this CRS here. 15 north, nat 27. I'm going to enlarge this column here. And what do we have in 15? So again, I've got the one in feet US or the general one in meters. So let's say I want to use the one in feet US here. So let's go for this one. And eventually I've got the Louisiana State Plains Southern Zone. So I'm going to go and change this CRS again. So I'm entering Louisiana South, and it's in NAD 27. So that's this one I should use here. Okay. And just for this one, I'm going to hit the scan button again. So here you see that my resolution again is slightly different. And just for this one here, I'm going to scan it. And you see that again, the resolution has changed. So that to make sure that we're considering each volumes as individual. So now that this is said, I will import these volumes. And actually, because I want to save some time, I've already imported these volumes before, and these are the one listed in my project browser here in the volume tab to the left. So I'm just going to cancel this operation, but this is the way you would do your setting if you were to import multiple volumes with different parameters. So let's go for this step. So cancel this, and I'm just going to display my different volumes right now. So for now, I'm going to display them as 3D cubes so that you can see their relative localization in the 3D space. So we're in time again. And you're going to notice that even though they've got some individual CRS, so each one of them have got specific CRS assigned, if I'm leaving them this way, they won't be displayed quite properly. And to show you this, I will also import a culture. So you see now, okay, even though you don't have any reference, the volumes are just spread. I've got one tiny one down there, which is certainly not in the same area than the three other ones in there. And I want to make sure that they are all located properly. So I'm just going to enlarge this. And I'm going to import a culture so that we can visualize the Gulf of Mexico shoreline. So I'm going to hit on culture and import my shape line. So I've got this somewhere here. Okay, Gulf of Mexico, I've got the culture here, and I've got to import this one. Okay, unit is in meters, I guess. So, okay, and I'm going to display this one. So here is my Gulf of Mexico shoreline in red, and you can definitely see that at least some of the volumes here are poorly inputted. So for example, I've got the one down there, which would be like down in South America or somewhere, and definitely should be nearby the coast. And I also have this one here that is on the carbonaceous platform of Florida, which is mislocated. Potentially these two one relatively are correct, but I want to locate all these volumes properly relative to one another. The first thing I want you to check is going from the main toolbar here in the Unit CRS tab, is that each of these volumes have been imported with the proper CRS. So you can see the 4 volumes here, and each time to the right here, you can see the CRS that I've assigned during the import. So in this case, I've used the first one, UTMs on 16, And the two other one got BLM 16 and feet US, and 16 and 15, and the latest one is in Louisiana South. So they have proper CRS individually, but now the next step, if I want to locate all these 4 volumes properly relative to one another, consists into assigning a project CRS. So this manipulation of project CRS is not new, but this is something you may not really know how to deal with in PaleoScan. And if you've got, as in the case of this project, different volumes that are not located in the same CRS, you must you will have to locate your volume individually in the proper CRS and do what I'm about to do now. You're going to need to assign a project CRS. That's going to be the global reference for the project. So I'm going to go into File here and Project Properties. So if you've not done this while you were creating your project at first time, you can go back in here, Project Properties, and assign here a project CRS. So to do this, I'm going to hit on this third field here on the tiny globe icon. So I'm clicking on here, and in the list, I'm going to have to choose one of the 3 CRS that correspond to my volume. So in this case, I would like to assign, for example, the Louisiana South. So again, I've got to filter out, and the Louisiana South in NAT 27 is going to be this one here. I'm going to pick this one up, click on OK. So because I'm assigning a new project CRS, PaleoScan understands that I'm going to change my global framework, my global reference for my project. So it is automatically going to undisplay all items currently displayed in the 3D, and I'll have to display them again. So this is what it was telling me now. I'll have to do the same again. So I'm just going to start with the polyline, with the culture of the shoreline. So again, open in 3D. Here's my shoreline again. Coming back for my volumes, I'll do the same. So I'll just display the cubes. So there's one here. Okay, the second one here. Then again, this time this one, which is supposed to be in UTM 16, seems to be more nicely located. Sorry, this is 15 for this one. And now for the Louisiana South, here it is. It's different again, and I've got my 4 different volumes properly located. So I didn't display the different blocks of the BOEM classification here, but you can just observe that now the volumes are properly displayed corresponding to the location. So this was the first step I wanted to show you in this session. Now, assuming that your volume import has been correctly done, and assuming that, for example, which is not the case for this data, that you're opening a volume into a 2D viewer and you've got some blank display on your color bar, so something that would look like, for example, like this, okay? And you'd have just one spike on your histogram here to the right. Potentially, it would mean that you've got some spikes in your data. You've got some extreme values of amplitudes, either positively or negatively. And to be able to have a proper display, well, you would like to despike your volume to remove these spikes. So what you should do in there, so you've got different to do this. You can, from your 2D window here, right-click on the top bar and look for the despike option that is here. Or you can directly go from the project browser and do the same. So on the project browser here, you right-click on your volume name to access the context menu. And again, you've got the despike option right here. So if I'm clicking on this, PaleoScan is going to scan out the whole 3D volume that you're considering and tell you what are the maximum and the minimum values. So for this one, it seems that this one has already been despiked somehow or filtered, because you've got the exact same value positively and negatively in the amplitude. But if you were to look for some spikes, maybe you would have, PaleoScan would have detected some really high values, like something like this, for example, and very low values, like these ones. Of course, probably they wouldn't be the same number. And you would have just to reassign a number that you would like to filter in here. So say, okay, I want to make sure that there are no spikes beyond, beyond minus 127 and above 127 positively. So if you're doing this, PaleoScan is going to remove the spike from the volume. Now, if you want to replace these empty removed cell by some actual amplitude value, then you can interpolate. You can use these box here, and PaleoScan is just going to interpolate with a neighboring voxel to assign a proper value or something quite consistent to the voxels that you would have removed from the volume. And eventually, when you're done with this, you're going to click on save, and this can save you a lot of trouble for your color bar display, like here. So in this case, I'm just redisplaying my volume again, and you would have to reopen the new volume despite again, and the color bar display would be proper. Now, this was for the first step of conditioning. And the next step would consist, for example, if you want to run a model grid, and if you've got some faults into your system, next step would be to go through some structural interpretation. So assuming that you have no fault set or no consistent fault set from third-party interpretation, you could use what we name in PaleoScan the AFE, which stands for Automatic Fault Extraction Workflow, and try through this to automatically extract faults. So let's give it a try, for example, with one of the volumes that I've got here. So you can go for these at different locations. You can go in the faults module toolbar, where you'd have any tool adapted for faults in PaleoScan. Or you can also go into volumes, then the first icon, which is volume attributes, and in the list, find the same option. So we're interested into fault plan, fault thinning, and fault extraction. Let's go into the fault module toolbar again. So here, faults, I'm going to go from Seismic, which is the first step, supposedly, that you want to use. There are 3 steps in the AFE workflow. You want to start with the Seismic. And you may already know this interface. You may have already tried it before. And what's new in this version is this tiny stereo net display that is here in the corner, and you're going to see how to use it. So here, what I need to do is to display one of my volumes. So I've been testing this volume for you. So I'm going to drop this one. So you see that there are some faults in there. By the way, you can just stretch and squeeze your volume a bit if you need to. And what you're going to see is that for the full plane computation, which is the first step of the 3 steps of the workflow for the AFE, okay, then you can go in this TerraNet and click on the on button. So it's going to turn green, and you're going to have this kind of green feature display here that is showing you the range of the range of angle that PaleoScan is going to scan to detect your faults. It doesn't mean that it's going to only detect your fault for this dip, for example, but it's just meaning that the scanning disk, which is used in the workflow for the detection and for the creation of the fault plan, is going to be rotated only between these ranges of dip. Okay, so if you want to see directly the result of this, for example, if I were looking for low angle faults, and pay attention to these. It's a reminder, you may already know this, but the dip that you're seeing here, they are not real dip, okay? They are image dip. It means they rely on the pixel and the pixel shape. So, for example, a dip of 45 degrees is just going to be the diagonal of one voxel. It's going to cross one voxel diagonally. This is because you cannot expect having a real dip in here because you're considering, for example, a seismic that is laterally in space dimension and vertically in time. So it would be irrelevant for considering and expecting a real dip. So, for example, 45, I'm just going to reduce this because 45 is, of course, a bit exaggerated, and 85. And here doing this, you'd notice that the range of dips would be decreased and would be reframed. Managing the ranges of dip when you're computing the full plan may be very useful if you want to optimize the computation time of this full plan attribute here, which is the first step again for this AFE workflow. The full plane attribute is the longest attribute to be computed, and because there's a rotation of the scanning disk in every direction and at every voxel location of your volume, it may be really, really time consuming. And if, for example, you're sure you're not expecting any low angle faults, you won't bother entering a low angle for the minimum dip, for example. You just restrain yourself between something like 70 and 80 something, by 90 degrees, and that's going to be enough. Okay, so for example, this. You've got the same type of filter if you're displaying the time slice, for example. The time slice here. if I'm looking at the azimuth. So if I want to vary my range of azimuth, for example, if I'm expecting only faults in one direction, so I would, for example, do this, or let's say I want to get some faults between 0 and 90 degrees. So this is what PaleoScan would do. And you can directly rotate these range selection from the stereo net. You just grab the stereo net itself and rotate it, and it's going to help. So in this case, you see that my seismic here is the original volume that I've inputted. Well, I've extracted it, but it's original in terms of resolution. And because I want to improve my computation time, I may afford to decimate the volume by 2 vertically. Initially, the vertical resolution was 4 milliseconds. And because in this AFE workflow, and this is a really useful tip I'm giving you here, you can afford to decimate vertically very often. I'm just going to switch back to the inline again. Sorry, it disappeared somewhere. I'm not too sure why. I'm just going to re-input the volume again. And if you're noticing at this, actually, I've got already a good resolution. You're not really aware of the resolution I'm using here. It's not visible. But what I'm going to do is that I'm going to decimate this volume here to get things easier and better, actually. So I'm just decimating vertically. So I'm just quitting this menu for a second. I'm going to come back to it later. I'm just going to use a decimation attribute on live. So if you want to decimate, or this is what we name undersample, you're going to have to go into the attribute selection and pick up the very last attribute from the list, undersampling. And here again, I want to use this volume here, and I want to decimate just vertically by 2. So I'm going to enter this. I can have a preview quite quickly. If I want to visualize the resolution, by the way, I can still zoom in. And in the properties relative to this viewer here, so the properties are here to the right. In the properties, I can go into interpolation here and switch from bilinear to known. And here I'm going to see the actual voxel behind the information. I'm going to do the same for the preview viewer here. So back to properties, interpolation, and switch to bilinear to known. So if I'm cross-navigating, I'm going to get aware that I've decimated vertically by 2. And it's going to be perfect for the sake of the AFE workflow. So I'm going to run this. So I'm undersampling because my volume is not too big here. It's going to be quite fast. Okay. And now I've got my undersampled volume here. So I'll open again the AFE full plane. So I'm going to come back to my interface. And now, because I've got a lower volume of lower resolution, then I'll perform my preview, and it's going to be a bit faster than it would have been. So, okay, let's say I've used my my preview for the range and for the range of dip and azimuth. I've adapted, for example, my ranges, for example, like something to 87. And I want to have a preview just for the first step of the workflow, which is the full plan computation. Then I just put my cross navigation cursor where do I want to have my preview. I click the preview button here, and I'm going to go for the preview. And here we go. So this is the type of result that we would have here in this green box that you can see on the panel to the left. Okay, so you can see some signal of fault probability here in red. And this is where the fault would be extracted. By the way, here, this display has been normalized compared to the previous version of PaleoScan. This is also an improvement. You see that you've got a normalization line in here that is going to get rid of the background gradients of amplitude of the full plan here, and allow us to remove some noise and have a clear vision of the deformation. So you can have a test with the two, but usually it's improving things quite a lot. I'm just going to have a last try for this preview using the other parameters that we have. I'm not going to explain too much what we've been improving in these other parameters because it's really subtle. So you'll notice that there is a new thing here, which is auto merge. It's quite minor, so I'm not going to talk to it. And we've got different method for the thinning method. Just what you need to know is that the Hessian was the former method, and now we've got a direct method that is slightly different. if you've got some more questions about this, don't hesitate to get in touch with us directly. And I guess there are also dedicated webinars about this. So I'm going to keep up the normalization and increase slightly the scanning disk. I want to remain on the same region and have a direct preview. So this time, because I've activated the fold thinning step and also the fold extraction step, I will have a preview for this green box of the output instead of in terms of fold creation. So let's go for the preview again. So again, as a general tip during this thing is being computed, just know that, okay, the larger the dip and the azimuth ranges, and the longer the fold plane is going to be, and the larger the scanning disk, the longer the computation is going to be. So the normalization doesn't change anything, it's just removing a background gradient, but it doesn't take much more time. And the fold thinning and the fold extraction steps are almost immediate. It's going to be a matter of a few minutes for the fold thinning, and it's going to be a matter of seconds for the fold extraction. So yeah, this is why I was saying, like, when you're doing this kind of a workflow here, it's good to condition to for example, to decimate your initial seismic volume. You can afford to decimate it by 2 vertically, and you're going to see that it's yielding some pretty nice results. Sorry, Steve, for not having covered your 2D workflow yet. Well, hopefully you can catch it on. This video is going to be recorded, by the way. Well, it's already recorded, so don't hesitate to ask for it later on, and you're going to see more things. So thank you for having here, Steve. So again, here's the result of the fold plane workflow. Sorry, the automatic fold extraction workflow, and you can see the folds that are going to be outputted here in the thinning, and they're symbolized in yellow here in the lines. So of course, varying your parameters, maybe you could catch more, and this is the type of output that you would get. Okay, done for these parts. Now what I'm going to show you is the next part of the workflow and the new things that are applicable to this. And we will pretend to create a model grid on this volume that I've showed you before. So should I need to create a model grid, which is used for the interpretation in PaleoScan, I go into model grid, press new, and I'm here in the model grid creation interface. And in this case, I want to go and create the model grid out of my original volume here. So it's 0705. Let's call it this way. So you recognize it. And first of all, I'm going to import some data here, some folds that I've actually computed from the fold plane. So what I'm going to do, I'm going to import these fold sets from an external project where these fold sets exist. So I'm going to the main toolbar, Project Data Exchange. And here I'm going to look for the project I want to catch my folds from. And here are the 2 fold sets that I have. So I've got 2 fold sets, and I want you to see the difference between these 2 fold sets. So I'm just selecting them, clicking on the tiny arrow to put them in my current project here to the left. This is now down. And now when I'm going to look for fold sets, you're going to see that these fold sets are available here. And just for one tiny thing that I'd like to show you again. Okay, so now you can see that there are some tiny arrows below these fold sets, and if I'm collapsing these arrows, you'll notice that there are a certain number of folds in each fold set. So the first fold set to the top here is the raw output from my automatic fold extraction workflow. It's the one without any manual refinement. So you can see that on a tiny volume here, I guess it was like maybe 40 square kilometer. And in depth, it was, in terms of second, it was maybe like 4 or 5 seconds. And you can see that we've outputted these number of folds. And with some help of PaleoScan, I've semi-automatically or manually edited these fold set to get rid of the wrong folds or to merge some folds that should have been merged together. And you can see that I've significantly reduced the number of folds. And this is this sorted fold set that I want to use here now for the model grid creation. So that's one thing I want to use. I'm going to drop this one here. And the new thing I would like to show you, and first I need to display this fold set in 3D so that you can see the intersection in this 2D viewer. Here it goes. So what I want to show you in the advanced option is this new option down there. So this new option is named Fault Zero Thickness, and it's activated by default. And this option allows you to have some tighter faults in the model grid close to the faults. So for example, some tighter horizons close to the fault. So if I want to have a look at this, I would have a preview of my grid with the default parameters. For example, somewhere around here, I've got a faulted area. So I just want to put my cursor here and see what happens when I'm using this fault zero thickness. And maybe a good exercise would be first to have a preview without the option, and then after activate it to see the difference. So I'm activating my test parameters. Okay, done. So now I'm not interested by visualizing the preview of the model itself. I'm more interested into having the grid itself. So here's the grid. So if I'm trying to point and interpret, okay, let's say, for example, this bright horizon here, which is pretty simple for the example. Okay, I'm just pointing and connecting. So what you're going to see is that at the location of the faults on the time map here, you're going to have some large gaps around the fault. And this is due to the fact that if I'm not using the option fault zero thickness, if I'm displaying the grid again, so let's display the grid again for a second. It should be faster now. Okay, then you'll notice that where I've got some faults going through, then PaleoScan may have not created some nodes at the vicinity of the faults because we were not to overlap one fault with some nodes. So because of these gaps of nodes, and you can also see it here, then we may lose some resolution in the time map. We are not creating necessarily tight horizon against the faults. And this, during the constraining of the grid, which aims at creating the geomodel, may have been quite annoying if we wanted to be really precise nearby the faults. Now, not using this option, I'm going to tick the box again. I'm going to make sure I'm still positioned at the same location, which is here, and I'm going to run the test parameters again, and we're going to see the difference. So let's go for this. I'm going to use the go to point and test parameters. So PaleoScan is going to have to recompute something out of here. So again, it's going to be taking a few seconds. And PaleoScan is going to recreate a new grid and is going to populate the grid with nodes everywhere, including at the fault location. And you're going to notice when we're going to try to interpret this horizon in particular, that the geometry of the horizon in time map at the fault location is going to be much more precise. Here we go with the new grid. So again, I'm going to try to interpret the same horizon and see the difference. I'm going to pick up exactly the same one. Not trying to fool yourself. So just going to connect this one. And here on this side, and here on this side, and again. So here there's a slight overlap in there. This is fine. I don't have time to just go and check. So what I wanted you to notice is that here, if you're looking at the fault location, then you're going to have some very, very small gaps only. And it's going to be, like PaleoScan is going to be much more precise regarding the fault location. So if I'm zooming in again, the small gaps you have, a few pixel of gaps, really correspond to the position of the fault itself. It's not related to the fact that we don't have any node at the fault location. So once again, if you want to see the grid, then you'll notice that there are nodes everywhere here. And also, okay, so in here, so you see, if I'm zooming in again, you don't have any gap anymore at the fault vicinity. So you're going to be much more precise in terms of horizon interpretation at the vicinity of the fault. So before I leave this interface and go for the next step, just notice that we've increased the maximum number of nodes in a grid. Before it was 60 millions, and now it's going to be I guess it's going to be 100 millions or 10, or maybe 10 billion. I'll have to make sure about this. But, well, we've significantly increased the number of nodes that you can create. So if you've got some very strong hardware, then you can give it a try with a much higher resolution. I'll go for the next step and pretend that I've built a model grid. So again, I'm going to transfer these objects quite quickly. So I'm going to pick up a model grid that already exists. So in this case, this is the one I want to create. I want to show you, so I'm going to transfer it. Here it goes. And I will open this model grid. I'll go for the latest interpretation, which is this one that I've been doing next week. So here I need a reference volume, which is not available in this project or is not explicitly pointed at, which is this one. So for a minute, I'm going to get rid of the 3D viewer of this one here and file these windows. So you'll notice with all the colored horizons here that this model grid has already been interpreted quite significantly. So I spent roughly 1 day in cumulated to interpret this grid. So all the marked horizon I've been interpreting, refining on what PaleoScan had automatically been doing. So you can see again here, so we're in Gulf of Mexico. I won't go for a geological explanation of the areas. I don't have time for this, but you notice your faults in normal system, and potentially that you've got some soil diaparism at some point. So you can see here, for example, from the base of the seismic, some diaparism popping up here. And now that I've got this interpretation, I can preview the model that I would extract out of it. So let's have a preview because we've got some new things about the preview. So the classic way of previewing is going to be the following, just the one by default when I'm going into the properties and clicking on activate preview. So you see with the color, with the colored areas that currently, if I were to create my geomodel at this current state, the geomodel eventually would be quite gappy, right? So I could still choose with this classic way of creating model to change some parameters, for example, the link probability here to kind of enhance the fulfillment of these geomodels. So let's change this parameter link probability back to 1. Okay, and let's another refresh of this classic preview model. So this is a new type of model that I would get by changing the parameters, but this is still a classic model that I would do it here. And you see that it's going to be gappy and jumpy and not really nice. So what I want to do is I want to try to create a geomodel only based on the horizon that I've marked, plus, and this is the new thing from PaleoScan 2020, plus taking into account the faults discontinuities that I've inputted in my grid. So for this, I'm going to go to Properties, Quality, and I'm going to choose Marked Only Faulted. So I'm going to go into the Marked Only Faulted and see the difference in preview that I have with these two models. So see what happens here. It's a much cleaner model. It's much nicer and it's much fuller of the extent of the model. So I can just go across, okay? Well, if I go across, I'd have to refresh the preview, which is a bit sad, but still. But generally, the model would be much fuller, much more synthetic, and following every relationship given by the colored horizon, the one that I've explicitly marked for the creation of my model. So again, you've got this here. And if I'm zooming in, you'll notice, for example, that PaleoScan accounts, and this is new from this version, accounts for the geometry of the faults to constrain the geometry of the model. So you can see that we've got some discrete displacement at the fault location here. And these guys are worked out automatically based on your marked horizon and the faults themselves. So this way I noticed that it can be really interesting for the same state of constraint, meaning the same number of marked horizon. It's interesting to create two types of model. One classic that is going to be really consistent with the geometry of the reflectors, whether the reflectors are continuous, and a marked only model that is going to be consistent only with the marked reflectors, but is going to be much fuller and is going to create some consistent geometry based on the marked horizon and the faults. So for you, I've already created these two models. I'm going to quickly import them again from my similar tools. So these two models are the followings. So the first one, the classic one, would be this one here. And the second one would be a multi-Z because we're able to master some multi-Z relationship with the marked only and faults model. So I'm going to import them both into PaleoScan. Okay. So it should be quite fast because they are small. It's just a time for a copy. Here we go. And now I've got my volumes imported. So if I look at my classic model, I'll have something like this. And I've enhanced the parameters. So you can see that, for example, my horizon, I'm just going to display this one into a blending viewer. Here we go. So you can see that this model here, if I'm going back to it, and the blending is going to be quite consistent with the seismic, whether the reflectors were properly catched or were properly caught. Okay, for example, in here in this interval, I've got some nice classic model, and the geometry of the model is quite nicely following the reflectors. But now if I'm going to go at some points like here, where the amplitudes of my seismic are not so nice, for example, in here, then the geometry of the classic model is not so good. So better maybe taking a model which is from marked only here. So if I want to show you this, I will just open a multi-Z, and you're going to see in the multi-Z here, okay, that's the geometry at the level of the low amplitude reflector is going to be much simpler, but is going to be much more following the seismic. So now, based on these two different geometries of model that are being done by two different ways, I may want to create some horizon stacks and some composite horizon stacks. So horizon stacks that would be created from one model for one seismic interval and for one other model for another seismic interval. So if I were to do so, I just have a few minutes left, so I'm going to show you quite quickly this so that you can understand the concept of this. I'm going to be back on my, this is interesting here. I'm going to be back here in my geomodel creations. For example, I'm taking the classic model, which is the one on top. I'm just going to go and display a background. So this is what you can see here. I'm going to enhance the interface. And for example, I've picked up the classic model here, the one on the top. And I want to create some horizons in there. And you can see that if I'm again in this interval, for example, with the low amplitudes, around here, I'm just going to decrease the density of horizons, so 50, for example. Then here we're not necessarily nicely following the reflectors. So because of this, we may end up with inconsistent mapping in the end if we were performing some mapping on the horizon stacks. So maybe in this interval, I would prefer using the other type of model. So in this case, I would have to select the multi-Z model. Again, I'd have to find a background again. Okay, and see what happens with this geometry of models. So the multi-Z with the one with the marked only and the false, and see what happens. Going back into this interval here and zooming in again. And then now you can see that even though we're not necessarily consistent with the polarities, we're much more, like we're creating some more coherent geometries for this interval where we've got no clues about how the seismic behaves. So this way, I could create several horizon stacks of several types in this seismic interval. For example, from top, I could use the classic model geometry because the reflectors are quite nicely imaged and quite continuous. Then for this interval I'm showing, I will use the multi-Z. Down there, I could use again the classic model because we've seen that the classic model is quite consistent, following the polarities quite nicely. And for the bottom, because I don't have much information, maybe the multi-Z model will be interesting as well. So what I've been doing for you, I've been creating these horizon stacks, and I've been extracting the horizon stacks, the horizons of these different stacks, and listed them. Again, to save some time, I'm going to import these horizons from a project where they already exist. So it's the same project again. I'm going to look for horizons, and you see here I have a list of horizons that are derived from different horizon stacks that are themselves derived from different geomodel and different geometry of geomodels. So I'm importing them. And what I want to do eventually is a composite horizon stack made out of these two types of horizons derived from the two types of geomodels, adjusting the geometry relative to the interval of the seismic where they are more say relevant to be used. So we're approaching the bottom of the list here. Almost there. Done. So the import is done. And now if I want to go into my list of horizon, here they are. And you'll notice with the name, so for example, this one and this one, that these horizons are derived from different horizon stacks, which themselves are derived from either the classic geomodel. Okay, so these two are from classic, so they're from top and bottom, or if I'm going towards the bottom, for multi-Z geomodel, depending on the geometry I wanted to use in the different seismic intervals. So know that this is carefully selected. I will show you what I wanted to show you. And we're already in the proper module toolbar. I want to create a composite horizon stacks. So I will click on this option here, horizon stack from horizons. Open this interface. Okay. I'm going to just select a reference volume that will determine the resolution of my horizons in the new stack. And I can squeeze this, this volume down a bit. Okay. Let's go for it. And now I'm going to have to input all the horizons here that I want to use to create my composite horizon stacks. So by the way, the two last horizons from the list are directly outputted from the model grid directly. They are not outputted from a geomodel, so they are really consistent with the polarities of the grid. Just for a tiny detail. Just going to drop these horizons in the list. So it's going to take again a few seconds so that PaleoScan can list them up in there and display them. It's going to be all of a sudden, it's going to be releasing them and they're all going to be there. So don't worry if you're having this kind of a display at some point. It's just going to eventually be dropped down. I'm just a bit circumspect about the fact that usually it's supposed to be faster. So I'm not sure why this time. Okay. It was a bit slow. So there your horizons are being listed. And you see that I've got my two horizons on top that I derived directly from my model grid. So they are on sharp polarities, very consistent with polarities. Here being displayed now are horizons that are derived from a multi-Z derived geomodel horizon stack. Down there are horizon stacks that are also derived from multi-Z. Up there, what are being filled now are horizon stack from a classic geomodel. So you see that the geometry is a bit more irregular because we're strictly trying to follow the polarities here. And you're noticing that the horizons are not listed initially in the proper stratigraphic order. So we are going to have to resolve them stratigraphically so that to have something consistent in the end. So I'm just going to do this just after. I'm sorry, it's 10:30 for me in France. So it's time to close to the end. I'm just sorry that this process is being a bit slow, but if you have a few more minutes, it's going to be quite interesting to see what happens in there. So I'm just going to sort with this tiny Z option in green here. I'm going to sort vertically the horizons. So I'm clicking on this, PaleoScan is going to sort them out. And down, I'm just going to, if you need to move manually some horizon in the list, you can still do this. See, I'm doing this. And then I'm going to save this one. So if I want to save this one, just save the horizon stack here. I give it a name, for example, Composite horizon stack. And it's derived from, I'm not going to be more precise on the name, but it's derived both from multi-Z and classic model. So here we're creating a horizon stack. And because on each of these horizons, I've already mapped some RMS amplitude, and you see it in the title, I've been doing this ahead of time. Then in the created composite horizon stacks, then all my horizons are already going to be mapped with some RMS amplitude signal. And actually, I believe that these processes are taking a bit longer than usual because my tiny modest laptop is being a bit full at this time. And therefore, well, PaleoScan takes a bit more time to store things in there. Here we go. So here we've got our composite horizon stack ready. It's over here. And I'm going to close things now, just displaying my horizon stack. Plus, just to get a reference, the seismic. Okay, I'll tile them, sorry, vertically, like this, for example. And zooming in, I'm just going to apply a more suitable color bar with some auto contrast. And now if I'm going down the series, so it's the C bottom, I'm going down, you're going to see the mapping of the RMS amplitude. Opa, it's time to close to the end, definitely. And going down this way, you can see that we are following the different geometries of the stack with the composite. So we can potentially see some items in the RMS amplitude. For example, here, there may be something interesting. And going down the list, I'll be able to consistently scan my seismic volume according to whatever, see here, something nice as well, according to the geometry of my horizon stack. So this is all for the 3D workflow. If you've got a bit more time, I'm just going to go quickly through the 2D. It's going to be very fast this time. I'm going to quit this project and open another one quite quickly, just so that to show you the new things. So it's for the sake of Steve that is going to be looking for this video later on. So we're going to be nice to him. I'm going to actually create a new project directly. So test 2D. I don't need a CRS in this case. I want to go as fast as possible. I'm going to import a few 2D lines just for the example. So here you recognize this interface. I'm going to look for my 2D lines. So this time I don't want volumes. I want 2D lines, and I will pick up these guys here from Maui, offshore New Zealand. Here they're listed. In this case, I don't have much things to do. So I can directly go for the import. Done. So my 2D lines are here. Without showing them to you, I'm just going to create a 2D line set, which is the step I need to do for creating a 2D model grid. And the new things I want to show you is in the 2D model grid. So I created 2D line set. So here is the shape in time map of my 2D line set. So it's quite tiny for the example. So I could cross navigate through them to see the different lines. Okay, I'm going to save them. Okay, save. This is fine. Pretty simple names. And now that I've got a 2D line set, I'm able to create a 2D model grid. So let's go for the 2D model grid creation. So what's new in here in this interface, once I've selected my set, again, it's displayed here. Once I've selected it, the new thing in here, it's in the advanced option, is that you've got the possibility of automatically connecting the reflectors of different lines together, as long as there's no too much mistie in between the lines. So trying to answer Steve's question, in here, we're able to analyze the mistie during the interpretation. But if there's two mistie at first, the auto connection in between the lines won't be possible, and the user would have to edit it manually. But just if there is not too much mistie, if the mistie is slight, then using this option, auto interp with connected lines and computing your grid, okay, then you're going to notice that once the grid is created, then I'll be able to select some reflectors, and they will be automatically propagated in between the lines. So it should be quite fast again, because I've got only small lines. And on top of this automatic propagation of the reflectors in between the different lines, that was not possible before, we've got another thing that I would like to quickly point you out. And it's very simple, but it can really help. Okay, we're done. So let's say I want to start interpreting, for example, in here. So if I got this reflector here, for example, I'll try to catch it, and notice something has happened. So if I'm looking in particular on the time map, and I will do something on purpose. Okay. I'm doing on the time map, if you're looking closely, PaleoScan has started to automatically propagate my interpretation, my small interpretation on this line here, which is kind of west to east, to the other line that is more like northeast, southwest. And if you're looking at what's happening in here, if I'm looking at this situation, you're looking that PaleoScan has been interpreting this one here, okay, this horizon, this reflector, and there is a small like yellow patch here, and this yellow patch corresponds to the intersection of the same reflector that is automatically connected on the line intersecting at this position. So if I'm looking at the line intersecting at this position, it's the line here to the right, you're going to see that PaleoScan has started to interpret this horizon automatically so that I can directly jump to this line and continue the interpretation. And you're going to see that here my mapping, my time map, is going to be evolving according to so. So the auto-propagation is a new thing, auto-propagation between the line. And this display of the intersection is another good thing to have, and this is another new thing, because if I'm zooming out on the time map for a second, let's say you're going to start to, for example, interpret a reflector on this line, then on this line, and then on this line, then you're going to loop your interpretation. And in the end of a loop, often, especially when you've got some wedge geometry like this one, so you've got thickness variations in there, you may have some reflectors down the wedge that are going to be multiplied, got more reflectors. So you're going to interpret, for example, these reflectors down the line, and then going to go to the next intersection, then change the line, go to the intersection, and then when you're going to loop up here, at some point, often you end up with some vertical shift because you selected the wrong reflectors. And having this type of intersection display allows you to anticipate a bit more if you're starting to drift away from your initial reflector or not. Now, as for the Misti, well, here I've only drawn one reflector. I'm just going to draw a second one. So you see for the sea bottom here, if I'm looking out at the time map, well, all these sea bottom has been automatically interpolated on a huge part of the line set here. Okay, where it's not have been interpolated is because we've got some gaps like the one we see here, and we have to keep working manually. But in the end, you can apply this Misti correction, and this is the thing that already exists into the 2019 version. You're going to have at the very bottom right of the interface here a shift on off. By default, it's off, and you can put it on so that the Misti between the line is corrected. And you can particularly see it on the intersection line here. See, you've got the intersection with one line on the side, the other line intersecting on the other side, and you can visualize the Misti. And clicking on this option here, then you can apply a Misti correction. So this Misti correction is applied on any reflectors that you would have marked on your model. Okay, so that's for the 2D. And I'm arriving at the end of my presentation. So I'll just return quickly for one slide of PowerPoint for the recap, for you just to get what we've been going through. So yeah, here what we've seen together as new things in the platform. So for the data conditioning, when you're importing your seismic and your volume, we've seen that we're able to manage the CRS in meters of feet. We're able to change the parameters of multiple seismic segue upon import, so that to avoid you to have to import them one by one and adapting the parameters every time. We're able to put to apply some volume despiking to avoid some wrong color path displays. We've tried to improve our AFE workflow for the automatic detection of faults, and in particular adding up this green feature that is allowing you to better anticipate the range of dip and azimuth that you want to extract or visualize. Then for the interpretation itself, the model grid is now better shaped, let's say, and is going to be tighter against the faults. It's going to be allowing you to have more precise time map right from the grid. And also you can put some more nodes. It's up to 1 million nodes here. You've got the information here. We're able to create some multi-Z geomodels, so only based on marked only, and the faults, which is new in 2020. And you can see, for example, in this tiny image here, that we've got some multi-Z relationship with frost faults in this example. In the output, I've especially talked about the horizon stacks, so we can create some horizon stacks that are going to be up to 10,000 horizons in there. And we can create some composite horizon stacks out of different horizons that would come up from different geometries of geomodels. Oh, something I didn't show you, but we're also able to manage the geotiff. I skipped this just as a matter of time. But you can save, for example, a horizon and save it as a geotiff right now. This is available from the context menu of any 2D viewer. So have a look, try to look for it. You'll find it, I'm sure. And finally, about the 2D interpretation, we've seen right now that in the model grid, when we're creating the grid, PaleoScan is now able to automatically connect the different reflectors, well, same reflectors, but for two intersecting lines. Well, assuming that the reflectors are not too shifted vertically. The Misti is not too big. And okay, this is what is circled in blue here in this tiny image. They were able to visualize the position of the horizon, the same horizon, at the intersection to better anticipate and have a better interpretation in 2D. And something I didn't talk about, but the 2D lines are now able to be inputted into our calculator. So that's the icon in the main toolbar with the tiny plus, minus, times, equal button. So you're able to use this calculator and use the 2D lines on the calculator to perform some calculation, attribute calculation, or things that you would like to do directly in there. It was not possible before, and it's possible now. So here I go. I'm at the end of my presentation. I'm just going to have a look at your, if there are some more questions. Have you heard a pop-up? Yeah. And thank you for your attention. Sorry again for this last technical issue that I had. If you need to contact me or anybody, there is the general contact email address, so contact@eliis.fr. And if you want to personally ask me for some questions about this session here, you can go at sven.philippe@eliis.fr, and you'll be very welcome. So again, sorry for this last interruption. I hope you've enjoyed the rest of the presentation. And yeah, I wish you a good summer for those of you in the Northern Hemisphere. And yeah, enjoy your day or enjoy your night. Have a good evening for those of you in the East. And